Hello, in this video we will do a short review on Calculus 1 and I will solve all problems on the practice final exam. Firstly, let's talk about the theory. So, in Calculus 1 we study two main problems, the tangent line problem and the area problem, right? The tangent line and the area problem. What is tangent line problem? So we study how to find the equation of tangent line, right? Suppose that you have some curve in here and you have some point on the curve and then you want to find the tangent line, right? This is x0, the function is y equal to f of x. So the equation of tangent line is y equal to y0 plus f prime at x0 times x minus x0, where the derivative is the slope, right? Derivative. And that at the same time that is the slope. And we know when we study, derivatives, derivative is slope, derivative is the rate of change, instantaneous rate of change, right? Instantaneous. So, it is important, and we study a couple of problems how to work with instantaneous rate of change. But basically, that is tangent line problem, right? The second problem is the area problem. So we learn how to find area of a region enclosed by the graph of the function on some interval a and b. So basically, we need to find the area of this region. And in the last chapter, we study the area is nothing but, definite integral from a to b, f of x dx, right? Where the function is f of x. We learn how to use Riemann sums to find this definite integral. And finally, we learn, the first and the second fundamental theorems of calculus. And we evaluate this definite integral using antiderivative of the function f of x. So that is f of b minus f of a, where f of x is an antiderivative of f of x. So this is about, two main problems that makes calculus and pre-calculus different. Okay, but overall in this calculus course we study four modules. The first one is limit, right? First is limit. Second one is continuity, and then differentiability, okay, and finally we study integration. So for limits, we always need to remember that, when you consider limit of function at some point, you need to consider two sides, right? The left limit and the right limit. I always say one side limits, right? One side limit. So if the left and the right limit are equal, then the limit exists. Okay, don't forget that. I write short left and right limits, right? Okay, how about continuity? When you move from limit to continuity, you need something else, right? At least for a function to be continuous at some point, that point should belongs to the domain of the function, right? And equal to the function value. So that's why, this is the condition for function f to be continuous as c. We say we define the function f as c. That means c belongs to the domain of the function, and the limit exists and equal to the function value. So in that case, the function is continuous. Okay, so that means the function might have limits, right? But not necessary to be continuous. And after that, we study differentiability. We study the first and second derivative, and we learn, you know, different applications of the derivatives. So let me remind you the definition of the derivative of function at some point c. So that is the limit of f of x minus f of c divided by x minus c when x approaches c. Okay, or sometimes you may see the following definition: limit of f of x plus delta x minus f of x. In this case, delta x delta x approaches 0. But in this case, that is the derivative of the function at some point x. So if you replace x with the c, so you go back to the first definition. All right. The derivative is defined via limit, right? So of course you might think about the left derivative and the right derivative. Does that make sense? Uh, like this. Okay, so I have, for example, I have this function, and then like this. This is the left derivative. The left tangent line is the right tangent line, right? They are not the same, so the function is not differentiable at this point. But if you have a very good function like this, and you consider some point here, this is the left tangent line, this is the right tangent line. Yeah, it looks like they are the same, so the function is differentiable. The left limit and the right limit means it's about in this case the left limit and the right limit are different. Look at that, right? The slopes are different, so the function is not differentiable. And we learn applications of the first and second derivative. Let me write that in here. Application of the first and the second derivative. As I don't do review on the differentiation rules because that is just rules, right? So we need to have integration table, differentiation table. I will remind you all the rules. But basically, we use rules at tools to study applications of the first and second derivatives. So for the first derivative, you might find different informations from that. So I can find critical points. Let's remind you that where the first derivative equal to 0 or the first derivative does not exist. Why do we need critical points? Because they give us information about extrema of the function, right? So we need critical points because we need to find extrema. Okay, for extrema, we have two kinds of extrema: global extrema and local extrema. Or sometimes we say global is absolute extrema. Okay, and this is relative. To find global extrema, we need to find all critical points, right? Of course, in this case, we know how to find global extrema on a closed interval. And then, we evaluate the function value. At critical points. And endpoints. From there, we can find, the greatest and the smallest as minimum or maximum, right? But in order to find local extrema, we need extra work. So once we know critical points, you need to make the chart for the first derivative. So the chart looks like this. The first row is about the x. So you write all the domain and special function in here. Okay, domain and special point, sorry. So I mean critical points or points where the function is not defined. Okay. And second one is, you find information about the first derivative, and the last one is about second derivative, the function. So, suppose that, you have some special points in here, two critical points, like let's say x1 and x2. Let me write here, x1 in here and x2 in here. And if x1 and x2 are critical points, so the first derivative will be, you know, 0, or maybe it does not exist, right? Or maybe I write here, maybe it does not exist, so we write like this. So in this case, you have three intervals. You have to determine the sign, plus or minus in here. Okay, I suppose that we have like that, right? Minus, negative, negative, positive. We know that when the first derivative is negative, the function is decreasing, right? And then, when the first derivative is greater than 0, the function is increasing, and then when the first derivative is less than 0, the function is decreasing again. So based on this chart, we know the function attains local minimum in here, right, and local maximum in here. And not only that, we know the intervals where the function is increasing right here and decreasing right here. Does that make sense? So, that is the applications of the first derivative. And for the second derivative, we may get, information about convexity or concavity of the function. Convexity, concavity. And of course, we also know about, inflection points, right? And we may test axiom. If you have, you have critical points, right? And you don't want to make the chart for the first derivative. You may differentiate the function the second time, find the second derivative. And when the second derivative at critical points less than 0, that is maximum. If the second derivative at that point is greater than 0, that is the minimum. But when the second derivative is 0, so this is inflection point. We don't have any information about convexity, concavity of the function. Okay, I will write here convexity when the first derivative greater than 0, concavity when the first derivative less than 0. Inflection point, the first derivative equal to 0 or does not exist. So basically, we say, inflection points are points where the function changes convexity and concavity. Okay, it's very similar to the case of critical points. Derivative does not exist or equal to 0, but this is about second derivative. Okay, so we have different rules in here, differentiation rules. No, but the most important one is the chain rule. Let's write product rule first, right? I write fg plus fg and I have f derivative, g derivative. And then the quotient rule, fg minus fg over g squared, and then f derivative, g derivative. And the chain rule, that's f derivative evaluated at the inside times the inside derivative, right? I think that is the main rules. And for integrations, I think I already talk about the area problem. So we will pay more attention on the area problem, and the most important technique in integration is substitution. And substitution is what? That is the the opposite, right? You will say here you have the chain rule. So for integration you have substitution. With integration, if you see something like that, so you put the inside function equal to u. Okay, that is about substitution. You see that when we solve example. So I think that is the picture of calculus 1. Okay, so we start from two problems, tangent line problem and area problem, and we use the limit in here. And so that's how uh, you see the evolution, from limit to continuity, from continuity to differentiability, and then you consider integration as an inverse process of differentiation. All right, so I think now we are ready to move to examples, okay, in the practice final exam. The first example, find the limit 12x plus 10 over x plus 5. So when you see a limit, the first thing you need to do is plug the point into the function, right? Here your point is -5. You plug -5 into the function, you would get 0 over 0. What does it mean? That means -5 is common 0, right? You might factor the top and the bottom. Okay, so the limit is equal to limit of, let me factor, right? I write x plus 5 in here, and then I have 2x plus 2 divided by x plus 5. X approaches -5. And of course, now you might simplify x plus 5. You get limit of 2x plus 2. X approaches -5. And you plug -5 into this. You get 2 times -5 plus 2, which is -8. That's the final answer. So I think you might meet the difficulty in here, right? When you factor. But again, you might use long division, whatever you want. Okay, long division. Or you might do a technique like this, right? If you have quadratic function, you just take x plus 5 out, and then you consider terms from the highest to the smallest. Here you have 2x squared, so here you already have x. That means this term should be 2x, because 2x times x will be 2x squared, right? And you already finished with term with the degree 1, and then you move to the free coefficient. You have 10 in the original, but here you have 5, right? So that means this term should be 2. That's it. Okay. All right. I will not give you many problems with limits. We still have different techniques, but that is the one we need to do on the final dividing technique. Okay. The second problem, find the equation of the tangent line. Okay. Find the equation of the tangent line. So that means you need to find the first derivative. So your function is x plus 8 over x minus 1, and the point is x equal to 1 over 2 and y equal to -17. They already gave you the y, but in case if they don't give you the y, you need to find it by plugging x equal to 1/2 into the function, right? And I find the y, for example, 1/2 plus 8 over 1/2 minus 1, so you get -17. Don't forget that. Okay. All right, so I need to find the first derivative because the equation looks like y equal to y prime y0 plus y prime at x0 times x minus x0. So that means I need to find the slope, right? Derivative. Y prime equal to, I use the quotient rule in this case. So I have x plus 8 derivative times x minus 1 minus x plus 8 times x minus 1 derivative. I very recommend you to write a formula and just apply the formula directly, and then in the second step you might simplify. Okay, and don't forget parentheses. X plus 8 derivative is 1, so I have x minus 1 minus x minus 8 derivative of x minus 1 is 1, but I always keep parentheses. Look at this, and please do not simplify this because that is wrong. Okay, do not do that. Let's simplify on the top. So you get x minus 1 minus x plus 8. Negative minus 8 is plus 8, right? X minus 1 square. So you get x minus x 0, you have 7 over x minus 1 square. And now you plug 1/2 right here into the derivative to find the slope. I write the slope equal to 7 over 1/2 minus 1 square, which is 7 over 1/2 square. So 1/2 square is 1/4, right? Divide by 1/4 means, multiply by the inverse. So I have 7 times 4 is 28. So I have equation equal to, okay, y prime with y0 is just negative 17, right? Negative 17 plus 28 x minus 1/2. You simplify that, you get 28x minus 14 minus 17, or that is 28x minus 31. This is the equation of the tangent line. Okay. Now let's move to the next example. Use the product rule and quotient rule, okay, to find the derivative. Now differentiation rules. Okay, I have function y equal to 7t to the 4 cosine t phi y prime. So it's obvious that we need to use the product rule. Okay, but again, right, what is the product rule? Please write it down, because I know, and I have seen that students write it fg derivative equal to f derivative g derivative. This is wrong. Please don't do that. Okay, so once you have formula, the function f is 4t to the 4 70. You don't have to pay attention on 7 because that is just coefficient. You might take that out, right? So you might think, yeah, f is t to the 4 and g is cosine t. So I write y prime equal to 7. I can take that out. T to the 4 derivative is 4t cubed cosine t plus t to the 4 derivative of cosine is negative side, right? Okay, negative side t. I tell you this, right? As I mentioned several times, I accept this solution. You don't need to simplify that if you are not asked to do. Okay? So we're done with this problem. Let's move to next one. Again, find the derivative of the following function: 6 square root of x plus 9 ninth root of x. It's very simple. We use the power rule. Okay, the power rule says you have x to the p derivative is px to the p minus 1. But for this problem, before you apply the power rule, you need to convert these functions into power functions. So you have 6 x to 1/2 plus 9 x to 1 over 9. From here you get a y prime equal to 6 1 over 2 x 1 over 2 minus 1 plus 9 x times 1 9, sorry, x 1 over 9 minus 1. Please don't skip this step, right? And then you simplify this, you get 3 x to negative 1 over 2 plus x to negative a over 9. You are done. Now let's find the second derivative of the following one: y equal to x sine square x. So you need to differentiate twice, right? The first derivative equal to sine square x plus x. Derivative of sine square. For that, we need to use the chain rule. So that is 2 times sine of x times cosine of x. Right? Because the inside function is sine. Derivative of the inside is cosine. And then you differentiate one more time. Derivative of sine square, again by the chain rule, you get 2 sine x times cosine x. For the second one, you need to use the product rule. Okay, 2. So I have 3 functions in here. That's fine. We know how to do product rule with 3 functions, right? You just write gfh plus fgh plus fgh, 3 terms, f derivative, g derivative, and h derivative, right? So I write 3 terms right here. f is just x, but the first derivative of x is just 1, so it's 2 psi x cosine x. The next one, 2x psi derivative is cosine x times cosine x. The next one is 2x psi of x, and then derivative of cosine is negative psi of x. Okay, so you might leave the answer like this. Now let's move to applications of the first and second derivative. Let's find the global extrema of the following function: y equal to x cubed minus 3 over 2x squared on negative 3, 2. So we need to find all critical points, right? First, I need to differentiate the function. I get 3x squared minus 3x. I set this equal to 0. I get 3x, x minus 1, right, equal to 0. From here, I get x equal to 0 or x equal to 1. So you have two critical points. Both belongs to the interval negative 3 and 2. Then you need to evaluate the function value at negative 3, 0, 1, and 2. So at negative 3, you plug negative 3 into the function, right? The function is right here. So I get, let's see, 27 minus 27 over 2. So that is 27. Oh no, negative 27, sorry. So you get 27 over 2. I write 27. That is 3 over 2, negative 3 over 2 times 27. So I get 21, 6. So 81, I guess, over 2 with negative. Yes. 81 over 2 with negative. At 0, the function is 0. At 1, the function is 1 minus 3 over 2, which is negative 1 over 2. Okay. At 2, the function is 8 minus 12 over 2, so which is 6. So that is 2. From here, you can see that this is maximum and this is minimum. That's it. All right. Now, let's consider the function y equal to negative 5x cubed plus 15x plus 6. Let's find all local extrema, right? Find local extrema. So we need to make the chart for the first derivative. As usual, I need to differentiate this function. I get negative 15x squared plus 15. And I set this equal to 0. You might simplify 15. You get negative x squared plus 1 equal to 0. Or x equal to x squared equal to 1, right? So x is plus minus 1. Now you need to make the chart for the first derivative, and then from there you get information. So that is x, is y prime is y. The function is defined everywhere, right? So I write from negative infinity to positive infinity. You have two critical points, negative 1 and 1. At this critical point, the derivative is 0. So you have three intervals. From here, you need to decide the side of the first derivative. So I pick 2, I pick 0, and I pick negative 2, and I plug into the derivative. Don't forget this. We are working with the derivative right here. So at 0, the derivative is 15, positive. At 2, the derivative is negative. At negative 2, the derivative also negative. So the function is decreasing, increasing, and decreasing here. So you can find, local minimum, right, at negative 1. Now I plug negative 1 into the function, right? So I get at negative 1, the function is, let's say, 5 plus or minus 15 plus 6. So that is negative 4. At 1 is 5 plus negative 5 plus 15 plus 6 is 16. So that is my local maximum That is my local minimum. And from here, in case if they ask you the intervals, right, where the function is increasing or decreasing, where the function is increasing, so you can write that from the chart, increasing on -1 to 1, right? But the function is decreasing on -infinity to -1, union with the 1 and infinity. Don't forget that. Okay. So that's about the application of the first derivative. Now let's solve one example with the second derivative. Find the intervals where the function is convex or concave, right? All right, so your function is y equal to x to the 4 minus 9x cubed. You need to find the second derivative, but before that, we need to find the first, right? So you have 4x cubed minus 27x squared. And then the second derivative is 12x squared minus 54x. Okay. So you set this equal to 0. From here you get, you might factor 2x out. You get 6x minus 27, right, equal to 0. From here you get x equal to 0 or 6x minus 27 equal to 0. So x equal to 0 or from here x equal to 9/2. The function has two inflection points. You make the chart for the second derivative. So almost similar to the case with the first, but here you have second derivative, right? The function is defined from -infinity to +infinity, two inflection points 9/2 and 0. At 9/2 and 0, the second derivative is 0. Now you have three intervals. You pick, for example, here you pick 1, you pick -1, right? Here you may pick, okay, let's say 5. You plug these numbers into the second derivative right here. At 1, the second derivative is negative. At 5, the second derivative is positive. And here I also have positive. So the function is convex. Means look like this. The function is concave. Look like this. And the function convex in here. Look like this. I can write the answer. The function is convex on -infinity 0 union with 9/2 infinity, and concave on 0 9/2. Okay. In case if they ask you to apply the second derivative test to find axioma, you might start from this, right? You need to find all critical points. So you set y prime equal to 0. From here you get 12x squared minus, 4x cubed minus 27x squared equal to 0. You factor x squared out, you get 4x minus 27 equal to 0. So x equal to 0 or x equal to 27/4. And you plug 0 and 27/4 into the second derivative. Okay? Plug into y2 prime. So at 0, y2 prime is just 0 right here. Because now that is inflection point. No, just inflection point. At 27/4. So what do you get in here? You get 2 times 27/4 times 6 times 27/4 minus 27 is bigger than 0. So this is local minimum. That's how we can use the second derivative test. Okay, so in this final exam, I will not give you any example to graph the function because it takes a lot of time. So I divide in small pieces like interval of convexity, concavity, or phi intervals where the function is increasing, decreasing. I think that is good enough. That is not all about applications of the first and second derivative. I I will give you an additional or bonus question on application. So you might have one of the following examples. I mean similar examples. Okay. First one is the shortest distance. So we know that if you have parabola and you have some point here, they ask you to find the shortest distance, right? So we solve that problem on the lectures. So we know the distance between 2 points. That is, let's say between uh, x1, x2, and y1, y2. So that is square root of y1 minus x1 plus y2 minus x2 squaring here, right? So if they give you a point, let's say x0. Okay, I think it's not a y0. Let's say that. Let me fix this. Okay, so it's not a x1, y1, and x2, y2. So the formula looks like, let me erase this. So you have x2 minus x1 square plus y2 minus y1 square. Okay. So if you have x0, y0, so that means you fix this point, and then here is your x2, y2, but they will give you the equation of the parabola or whatever, right? So y2 is just a function of x2. So basically, this is a function in one variable, right? In order to find the shortest or the closest point, you need to find the minimum of this function. That's it. And you apply whatever right? So I will not give you, in detail. That is bonus question. Okay. Or another question maybe, so one of these candidates, right? Application of differential. We know that we use differential to approximate, right? To approximate function value. So actually that is linear approximation, and that is nothing but using the equation of tangent line instead of the equation of the function, right? So I can I write like this: function f of x is approximately equal to f of x0 plus f derivative at x0 and x minus x0. So you need to find the equation of the tangent line, and instead of the function, you might use this to approximate the function value. Okay, so I really recommend you to look at these problems again, right? And because they will be one of bonus questions, so 10 points. All right, so I think we finished application of differentiation in here. Let's move to the last topic, that is integration. So for the integration, I will start from recovering a function, knowing the first or second derivative. Okay, so now we have function f of x equal to 10x minus 4x cubed. Okay, okay, let's say f prime, sorry. And we know that the function value at 3 is equal to 1. Let's find the function f, right? So we need to recover the function knowing the derivative. Means you just need to integrate that. So I integrate the function f of x is equal to integral 10x minus 4x cubed dx. 10x gives me x squared over 2 in here, right? I will simplify later, don't worry about that. X to the 4 over 4, and then plus constant. So I simplify that. I get 5x squared minus x to the 4 plus c. That's my f of x. My job now is to find the c. So I use the initial condition, right? I plug 3 into the function and set it equal to 1. So I know f3 is 3 squared minus 3 to the 4 plus c equal to 1. So from here I can see, okay, let's simplify this, right? I have 5 with the 9 is 49, 45 minus, this is 81 plus c equal to 1. C equal to 81 plus 1 minus 45. So that is, okay, I think that is 37, I guess. From here, the function is f of x equal to 5x squared minus x to the 4 and then plus 37. It is pretty simple, right? And then let's solve a couple more examples on the substitution. So the next example would be indefinite integral of 2 plus 1 over t times 1 over t squared dt. So for this, I'll put u equal to 2 plus 1 over t. And I have du is negative dt over t squared. Perfect. Look at this. dt over t squared. So, after substitution, I need to rewrite my integral, right, in terms of new variable. So I write the integral is equal to negative u du. We have negative in here because, negative comes from here. Does that make sense? So this is just equal to negative 1 over 2 u squared plus constant. 1 over 2. U is 2 plus 1t plus constant. And we finish this problem. Let's do one more example with definite integral with substitution. We have dx over square root of ax plus 9. So you might put u equal to ax plus 9. From here you get du is a dx. You might change the integration limits from here. When x equal to 2, u equal to 8 times 2 plus 9 is 16 plus 9 is 25. Okay. When x equal to 9, you have 8 times 9 plus 9 is 81. Now you rewrite your integral, but using these new integration limits. Let's say this is I from where? From 25 to 81. Dx, you can find the x from here. Dx is du over 8. So I write 1/8, right? Du over square root of u. And we know how to do this because, square root is power 1/2. And you flip that before you want to use the power rule. So I get, u to negative 1/2 du. That's 1/8. U negative 1/2 plus 1 over negative 1/2 plus 1 plus c. And then, I'm sorry, here we don't need c because we already evaluated from 25 to 81. So 1 over 8 times square root of u divided by 1/2. So you might think, you might simplify that, right? Evaluated from 25 to 81. So that is 1/4. Square root of 81 minus square root of 25. It looks pretty nice. So 1/4, 9 minus 5. Oh, final answer is just 1. Okay. All right. So the last problem is the area problem. Find the area of the region, about it, by the graph of the function y equal to x plus sub x. Okay, on 0 pi over 2. So as usual, before you solve every problem, you have to make sure about the graph, right? You have to make sure about the graph, because if we don't know about the graph of the function, you might have this situation and you have positive area in here, negative area in here. Sometimes you need to split, you know, uh, the function, on different intervals. Let's say sometimes we need to consider the function on different intervals, right? So we need to make sure about the graph if it is above or under the x-axis. I tell you again, right? Without this step, you get a half. Even you get the correct answer, but you lost. They said you lost a half of the credit. No, that means you get only a half of the credit. Okay. So how to see that? Our function is y equal to x plus psi, and we consider on the interval 0 pi over 2. On 0 pi over 2, x is greater than or equal to 0, and psi of x is also greater than or equal to 0. Therefore, x plus psi of x is always greater than or equal to 0 on 0 pi over 2. That's it. So this step says, yes, the graph is above the x-axis. So now I know exactly the graph should look like this, And I don't care about, it is convex or concave, increasing or decreasing, but I know exactly the graph is above the x-axis. And the area is just equal to definite integral from 0 to pi over 2, x plus psi of x dx. Does that make sense? And then you solve this integral and you get the answer you need. Antiderivative of x is x squared over 2. Antiderivative of psi is negative cosine. Evaluated from 0 to pi over 2. Okay, so you plug, pi over 2 and 0 into this, you get pi square over 8 minus cosine pi over 2 minus 0 square over 2 minus cosine of 0. So don't forget parentheses in here. Cosine pi over 2 is 0. Cosine 0 is 1. So I get negative 1 is plus 1 in here. Pi square over 8 plus 1. That's the final answer. So I hope that the video is useful enough for you to prepare to the final exam, and good luck.